Okay, so we are going to graph the function f of x equals the square root of x plus 2 minus 4. We're going to find its domain and range, and then we're going to find the equation of its inverse, and then decide if the inverse is also a function. The first thing that we want to do, whether you use your graphing calculator or just plug in random x values, but we need to create a table. So I'm going to go ahead and fill those in for us. If we take the values -2, -1, 2, 7, and 14, and like I said, you can either come up with these in your brain or you can graph the function and go to your table of values. But if I have an x value of -2, my y value is -4, and then I have -3, -2, -1, and 0. And essentially, these are just the points from least, starting with the least and moving to the greatest, the integer points that we see first on our function, on our square root function. Now, in order to find our inverse points, remember, all you're going to do is switch your x and y values. So we have a point -4, -2, -3, -1, -2, +2, -1, 7, and 0, 14. So what is this going to look like when we graph these values? How is this going to look to us? All right, so I went ahead and I graphed the points for you guys. And this purple graph, I know it doesn't look great, but this purple graph is our square root curve. And then the green graph represents our inverse curve. Now we need to decide, does this inverse curve represent a function? If you remember from Algebra 1, if you look at a graph and it passes the vertical line test, that means if we take a line and pass it from left to right across our graph and touch only one point at a time, then it is a function. And when I look at that green graph, I can tell, even though it gets really steep, it is a function. So we can use this notation, f inverse of x, for that graph. Now, what is the equation of f inverse? So how do we find that? So this is what we're going to do. Scroll down here. I've retyped the equation for you, and the steps are listed out right above. The first step is going to be that we want to replace our function notation f of x with y. So I start with y equals the square root of x plus 2 minus 4. Our second step is to switch the x and the y values. So x equals the square root of y plus 2 minus 4. And then our last step is going to be to solve for y. Okay, well, how do we solve for our y value? We've got to isolate it by adding 4 to both sides of our equation to start. That gives us x plus 4 equals the square root of y plus 2. And now I've got that y plus 2 stuck underneath my square root. And the inverse operation for square root, to undo the square root, is to square it. If I square the right side, I've got to square the left side. So we end up with x plus 4, quantity squared, equals, and our square root and our square, those undo each other. So we're just left with y plus 2. So we're almost there. We have to subtract 2 from both sides of our equation. And that gives us x plus 4, quantity squared, minus 2 equals y. Now, I know some of you do not like having your equation with your y equals on the right side, so we're going to go ahead and flip it around. It's just y equals x plus 4 squared minus 2. And like we said a moment ago, because our graph passes the vertical line test, we can use function notation here. But we have one little problem. Let's go ahead and finish writing this out. This right here is the equation of a quadratic, and a quadratic graph makes that U shape, and that's definitely not what our inverse looks like. If you look carefully back at your graph, we can see we only have half of a quadratic. We start at the vertex and we're only looking at the right side. So we have to figure out how to chop up that parabola so that we only have half of it. Well, and here's a simple trick every single time that you can use. Let's find the domain and range of f of x to begin with. So our purple graph is f of x. The domain always moves from left to right. So from left to right, our graph is moving, or it starts at -2 and goes all the way to positive infinity. And we actually do touch -2, so we put a bracket around that. And the range for this function starts at a height of -4 and goes up to positive infinity. So from -4, whoops, erase. From -4, that's not what I want, to positive infinity, that's our range. If you'll remember from the notes that we did the other day, every single function and its inverse, you can take the domain of f and it becomes the range values for your inverse. So our range values for the inverse function are from -2 to positive infinity. And if you take the range of your original function f of x, they turn into the domain values of your inverse. So how does that help us? Well, that green graph that we have up there starts on the left side at -4 and goes all the way to positive infinity. So we have to add that on to the end of our inverse function equation. So we're going to come down here and we have it all written out, but we're going to add on to it. Our x value has to be greater than or equal to -4. This right here represents our inverse function rule. Now, what I just said in words, I want you guys to go ahead and maybe type out or write out at the bottom of your note sheet, okay? This is what we're going to say. We have to restrict, and that's tiny, so let's make it bigger. All right. We have to restrict the domain since only half of the quadratic, I can spell sometimes, quadratic, represents the inverse. Okay, we have to restrict the domain because only half of that quadratic, that parabola, represents the inverse. We are going to use the range of the original function to help find the domain restrictions or the restricted domain values. Restricted domain values. Okay? All right, so where do we look? One more time. We have to restrict the domain since only half of the quadratic represents the inverse. What are we going to use to figure out what those restricted domain values are? We're going to use the range of our original function to help find the restricted domain values of our inverse. Does that make sense? Hopefully it does. Dadgummit. Eventually I'll be able to stop this.